Hi, Ms. Dong. For my culminating task, I analyzed the physics behind several scenes from Star Wars Episode 5, The Empire Strikes Back. Also, sorry in advance for going a bit long, but I promise it's worth it. The physics behind these moments are truly fascinating. In this scene, we see Yoda using the Force in order to lift Luke's submerged X-Wing from the swamp in Dagobah. Although the film provides no explicit distance for the vertical displacement, an estimate can be made by comparing the lift height to the height of the X-Wing. It appears as if Yoda raises the craft to a height approximately twice that of the X-Wing, meaning our net vertical displacement is 2 times the height of the X-Wing. According to Wikipedia, an online Star Wars encyclopedia, the X-Wing's height is 4.4 meters, meaning our net displacement is 8.8 meters. To analyze the dynamics of the lift, we consider the forces acting on the X-Wing. Only 2 forces play a significant role: the gravitational force, Fg, and the upward force exerted by Yoda, Fy. Air resistance can be assumed to be negligible due to the slow, smooth ascent, and of course there is no normal force since the craft is not in contact with any surfaces. Thus, the net force is, of course, the force Yoda exerts plus the gravitational force. In this scene, we see an inertial frame of reference being used. The scene's viewpoint is of an observer standing on the surface of Dagobah, which of course is stationary and non-accelerating. This allows us to apply Newton's laws directly without introducing any fictitious forces. Since there is no canonical value for Dagobah's surface gravity, we must consider a real-world analog. Dagobah's diameter of 14,410 kilometers, which we can get again from Wikipedia, is most similar to Earth's diameter at 12,756 kilometers. Thus, in the absence of contradictory information, it is reasonable to approximate that the gravity of Dagobah will be most similar to the gravity of Earth, as in 9.8 meters per second squared. And of course, for lift, we have that the force Yoda exerts must be greater than or equal to the force of gravity, meaning our minimum force is when the force Yoda's force equals the gravitational force. As such, substituting our values, we can get that the minimum force Yoda exerts is 98,000 newtons. And the only remaining unknown that we need in order to get the maximum force is vertical acceleration, which must be inferred from the observed kinematics, as currently we do not have enough information to obtain it. Because lift appears continuous and smooth, we can assume symmetric acceleration and deceleration, as in the X-Wing accelerates for the first t over 2 seconds and decelerates for the final t over 2 seconds. As such, we have in the acceleration phase, displacement will equal our initial velocity, which will be 0 because we're at rest, times delta t, plus 1/2 acceleration delta t squared. And of course here delta t would be t over 2 given our assumption. And simplifying, we get that delta d1y is 1/8 acceleration times t squared. In the deceleration phase, our initial velocity will just be acceleration times delta t, as vi1, of course, is just 0. And as such, we can find by simple algebra the delta d2y is 1/8 acceleration times t squared. Thus, of course, we have that the net displacement delta d net y is of course the sum of our 2 displacements. So summing them, we get delta d net y is 1/4 acceleration times t squared. And of course, by isolating for acceleration, we get the acceleration equals 4 delta d net y over t squared. Of course, we have delta d net y is 8.8 meters, and by analyzing the scene, we can estimate that the motion takes roughly 19 seconds, so we can use this as the value for t. Substituting values, we get that the acceleration is 0.095 meters per second squared. As such, using Newton's second law, we can get that the maximal force Yoda exerts is 98,960 newtons. Now, to test whether our assumption of symmetric acceleration deceleration is justifiable, we can compare two independent estimates of average mechanical power. Of course, the first method is by work and time. Of course, by the work-energy theorem, we have that work equals the change in gravitational potential energy, which by substituting our values, we get a value of 862,400 joules. Then using the formula for average mechanical power, we get that the average mechanical power is 45,034 watts. Alternatively, we know that average mechanical power is our force times our average velocity, where average velocity is our displacement over time, as in 0.46 meters. So substituting our values, we get 45,475 watts, meaning that our assumption is quite justifiable as both estimates fall within 1% of each other.
Oh, this is suicide. There's nowhere to go.
There, that looks pretty good.
That looks pretty good.
Yeah, you're doing nice.
Excuse me, ma'am, but where are we going?
Scene, the Millennium Falcon travels in a loop to enter a cave within the asteroid as it tries to evade TIE fighters. For simplicity, we assume that during the looping motion, the Falcon undergoes uniform circular motion. Because the Falcon is in deep space, we neglect gravitational force, as also the asteroid is quite small, as well as drag forces, and consider the only significant force during the loop to be the thrust force, which acts to change the direction of the ship's velocity. During the circular motion, this thrust force would then become, of course, the centripetal force, Fc. Right? So, using Wikipedia, we attain that the mass of the Falcon is 1.5 times 10 to the 5 kilograms, and its maximum speed is 291.67 meters per second. Since the Falcon is fleeing from the TIE fighters, it's of course reasonable to assume that it's traveling at its maximum speed. And of course, by analyzing the scene, we can estimate that it takes the Falcon around 12 seconds to complete one full loop, aka our period length. So of course, by using the uniform circular motion relationship, velocity equals 2 pi RT, we can get that the radius is 554.73 meters. As such, we can calculate our centripetal acceleration by, of course, just simply substituting our values and get that it's equal to 153.36 meters per second squared, from which we can calculate the g-force to be 15.65, which is far beyond realistic human tolerance. Real fighter pilots can only handle approximately 8 to 9 Gs for a short duration. Therefore, Leia, of course, remaining conscious during this maneuver is highly unrealistic. However, it is important to note that it's mildly more plausible that potentially Han Solo and Chewbacca remain conscious during the motion, as they are, professional pilots. And of course, by Newton's second law, we can attain that the centripetal force is 23 million newtons. Moreover, in this scene, we implicitly observe the motion from an inertial frame of reference, that being a stationary observer in space, watching the Falcon do the loop. This, of course, allows us to apply Newton's laws directly without introducing any pseudo-forces. However, it's important to note that the interior of the Millennium Falcon would be a non-inertial accelerating frame, meaning the crew would experience strong inertial pseudo-forces, pushing them outward during the loop. The extremely high 15.65 g-force further supports this conclusion that the scene, while really compelling, clearly exaggerates what would be physically survivable.
Delta, go now. All right, coming in.
In this scene, we observe a battle between the rebels and the Empire on Hoth, specifically involving rebel snowspeeders flying towards Imperial all-terrain armored transport, aka AT-ATs. The snowspeeders initially travel in a roughly straight path and eventually execute a looping maneuver, which, for simplicity, we model as uniform circular motion. In contrast, the AT-ATs travel linearly for the entire duration of the scene. The forces acting on each snowspeeder include the thrust generated by its engines, FA1, aerodynamic drag, FD, the gravitational force, FG1, as well as an additional upward lift force, F1, that keeps the snowspeeder in the air. Because the snowspeeders are in air, of course, they experience no normal force. Moreover, since the snowspeeders are traveling forward, we must have FA1 is greater than FD, and since the snowspeeders are airborne, F1 must be greater than FG1, and this is of course portrayed by the fact that the arrows representing FA1 and F1 are drawn longer than those representing drag and gravity, respectively. The forces acting on the AT-AT are the normal force exerted by the ground, gravitational force, Fg2, frictional force, Ff, and the applied engine force from Fa2. Since the AT-ATs are in motion, we have that Fa2 is greater than the frictional force, which is represented by a longer applied force arrow. And furthermore, since the AT-ATs remain on the ground, we have that the normal force equals the gravitational force, which we see by equally length arrows. From Wikipedia, the effective combat speed of a snowspeeder is 166.67 meters per second, and the mass is 7 times 10 to the 4th kilograms. Thus, we can calculate the kinetic energy to be, of course, 972,261,112 joules. Of course, you can then also calculate the momentum which would give us to be 11,666,900 kilograms per meter second. We can do the same for the AT-AT. By Wikipedia, we get that the velocity of an AT-AT is 16.67 meters per second, and the mass is 2.9 times 10 to the 5th kilograms. Thus, the kinetic energy can be calculated to be 40,293,891. Then, of course, we can once again calculate momentum and get that it's 4,834,300 kilograms per meter per second. These results make physical sense, as although the AT-AT is substantially heavier than the snowspeeder, the most snowspeeder's far greater velocity results in it having both higher kinetic energy and higher momentum. Moreover, since the AT-AT faces kinetic friction, we can suppose a hypothetical scenario in which the AT-AT stops applying force, as in Fa2 would become 0, which is analogous to the later scene where the AT-AT's power is lost. And with this, we can calculate how long as well as how far the AT-AT will travel before it reaches rest. Of course, it's important to note that in this scene, we have an inertial frame of reference fixed to the surface of Hoth. From this perspective, both the snowspeeders and AT-ATs move according to Newton's law, allowing us to analyze their forces and energy without having to introduce any fictitious forces. However, the interior of a snowspeeder would constitute a non-inertial accelerating frame, meaning the pilots would experience a significant inertial forces pushing them outward. Right? So horizontally, we have in this scenario that our net force is just the force of kinetic friction. By Newton's second law, of course, we get that. And by online research, we obtained that the coefficient of kinetic friction of aluminum on snow is 0.35, which is similar to the actual materials of the AT-AT. Since there is no canonical value for the gravity of Hoth, we must consider a real-world analog. Hoth's diameter of 7,200 kilometers is most similar to Mars' diameter of 6,792 kilometers. Thus, in the absence of contradictory lore, it is reasonable to approximate that the gravity of Hoth will be most similar to the gravity of Mars. Thus, the gravity of Hoth is 3.728 meters per second. Thus, we can get our acceleration is negative 1.3048 meters per second squared. Thus, we can apply our kinematic equations. Here, our initial velocity will be our normal velocity of 16.67 meters per second as we are trying to reach rest. So, applying our values and isolating for delta for displacement, we get our displacement is 106.49 meters. Then, of course, using our kinematic equations, we can solve for t. Isolating for t, we get that it's equal to 2 times the displacement over the sum of the velocities and get that it's equal to 12.78 seconds. Meaning that if the AT-AT stopped applying force, it would take 12.78 seconds for it to reach rest, during which it would travel 106.49 meters. Moreover, the scene shows some relative velocity. If we assume the snow speeders are traveling east at their respective value and the AT-ATs are traveling west, we can calculate the relative speed of the snow speeder to the AT-AT. So of course, first we need both in the same direction. 16.67 meters per second west is the same as negative 16.67 meters per second east. Thus, applying our formulae and the inversion principle, we can get that the velocity of the snow speeder relative to the AT-AT is 183.34 meters per second east. Finally, the scene demonstrates uniform circular motion with the snow speeder circling back to travel underneath the legs of the AT-ATs. As shown here, the orange box being the snow speeder is traveling, then it travels in this loop where we'd have centripetal force. It is important to consider that during the scene, the thrust force will become our centripetal force, and the circular loop is at a tilt, meaning that our centripetal force will be applied on the axis of the circle, while gravity and the lift force will be applied straight down and up respectively, as shown here. By analyzing the scene, we can estimate that the snow speeders complete the loop in 7.8 seconds. Thus, using the uniform circular motion relationship, velocity equals 2 pi rt, we can get that the radius is 206.91 meters. Thus, the centripetal acceleration is 134.26 meters per second squared. And the corresponding g-force would be 13.7, which is more realistic than the loop in scene 2, but still above the average g-force felt by fighter pilots. However, in this context, it is plausible that the pilots do not pass out, as they are depicted to be experienced individuals. Finally, we can, of course, calculate our centripetal force by Newton's second law and get that it is 9,398,200 newtons. And we see TIE fighters chasing the Millennium Falcon in space, with both traveling in a roughly straight path. In this analysis, we assume that both Millennium Falcon and the TIE fighter will be traveling at their maximal speeds, as it is a high-stakes chase. Since both crafts are in deep space, the only force acting upon them is thrust by their engines, FA1 and FA2, for the TIE fighter and Millennium Falcon, respectively. From Wikipedia, the max speed of a TIE fighter is 333.33 meters per second, and the mass is 2 times 10 to the 4th kilograms. Thus, the kinetic energy we can calculate to be 1,111,088,889, and the momentum would be, of course, 6,666,600. Similarly, from Wikipedia, we can find that the maximum speed of the Millennium Falcon is 291.67 meters per second, and the mass of the Millennium Falcon is 1.5 times 10 to the 5 kilograms. Thus, the kinetic energy is 6,380,354,168 joules, and the respective momentum would be, of course, 43,750,500 kilograms per meter per second. These results make physical sense. The TIE fighter has less kinetic energy and momentum than the Falcon due to its substantially higher mass and both crafts having similar speeds. If we define west to be positive, and assuming the Millennium Falcon is of course traveling at their maximum speeds, we can calculate the relative speed of the TIE fighter to the Millennium Falcon. Right? So, of course, using our formulae and the inversion principle, we get that the velocity of the TIE fighter relative to the Millennium Falcon is 41.66 meters per second west. In this scene, as TIE fighters pursue the Millennium Falcon through an asteroid field, one TIE fighter collides with an asteroid in what is effectively a perfectly inelastic collision. Since the encounter takes place in deep space, the only significant force acting on the TIE fighter prior to the impact is the thrust produced by its engines, and moreover, gravitational forces are negligible at this scale. The motion of the two bodies is relatively straightforward. The asteroid moves downwards, while the TIE fighter moves horizontally. Upon collision, the two objects adhere and continue together with a shared final velocity, which would look something like this. From Wikipedia, the max speed of a TIE fighter is 333.33 meters per second, and the mass is 2 times 10 to the 4 kilograms. From online research, the average speed of an asteroid is 1,000 miles per hour, which would be 446.04 meters per second. If we say down is south and the TIE fighter is traveling west, defining both of these directions to be positive, we can calculate the final velocity. Right? So we can get that the momentum of the asteroid is 26,822,400. Similarly, the momentum of the TIE fighter is 6,666,600, meaning our net or final momentum is the square root of the sum of the squares, which is 27,638,464.09. Thus, we can, by the conservation of momentum, find our final velocity to be our final momentum over the sum of our masses, which gives us a magnitude of velocity to be 345.48 meters per second. And to determine the direction of the final velocity, we compute the angle relative to the asteroid's southward direction, as in tan inverse momentum of the TIE fighter over the momentum of the asteroid, to give us 13.96 degrees, meaning the final velocity is 345.48 meters per second, south 13.96 degrees west.
I'm standing here in pieces, and you're having delusions of grandeur. You did it!
In the scene, the Millennium Falcon is seen traversing deep space, jumping into hyperspace to evade Darth Vader and the Empire. Its trajectory spans from Bespin to a nearby Rebel rendezvous point. Since no canonical distance between Bespin and the rendezvous point is provided, we approximate it using typical interstellar distances in the Milky Way. Online research gives us that the average distance between stars systems in the Milky Way range from 5 to 10 light years. So, taking the average, we get that a distance would be 7.5 light years, which in meters would be 7.05 times 10 to the 16 meters. In Star Wars canon, hyperspace is defined to be 0.99 times the speed of light, and in Star Wars Legends, the speed of hyperspace is given at 9.13 times 10 to the 6 times the speed of light. We assume the absence of acceleration since the scene portrays the Millennium Falcon charging up before instantaneously entering hyperspace. The time measured by an observer on Bespin can be calculated by distance over speed, which would be 7.53 years. Proper time experienced by someone aboard the Millennium Falcon can be determined using the time dilation formula of special relativity, and by simple algebra, we can isolate for proper time to be the coordinate time times the square root of 1 minus the speed over the speed of light. Substituting our values, we get a time of 1.06 years. Thus, while 7.53 years would pass for someone stationary on Bespin, only 1.06 years would elapse for passengers aboard the Millennium Falcon. It is important to note that these values are a bit contradictory to the Star Wars theory, with certain instances of the franchise suggesting that hyperspace only lasts for a couple of minutes. As such, we consider the hyperspace speeds of Star Wars Legend, which states that hyperspace travels at 9.13 times 10 to the 6th speeds of light. Applying the same distance, the coordination time would work out to be 25.74 seconds. And attempting to calculate proper time using the time dilation formula and simple algebraic manipulations, we would get the imaginary number, which suggests a physical inconsistency since special relativity of course forbids speeds greater than the speed of light. In this case, we have the time dilation formula itself would collapse, underscoring the impossibility of the depicted motion. Thus, while the Star Wars narrative may portray hyperspace travel as lasting only a few minutes, real-world physics dictates that at least a year would elapse during such a journey. And of course, it is important to consider the frame of reference when analyzing the hyperspace travel. Bespin serves as an inertial frame where observers measure elapsed time under standard relativistic mechanics. The extreme speeds considered in Legends would, of course, render the inertial frame assumption invalid and highlight the purely fictional nature of hyperspace physics. Finally, we can consider Newton's law of universal gravitation. While no specific scene in The Empire Strikes Back explicitly depicts a spacecraft entering a planet's atmosphere, it is reasonable to infer that such an event must occur for the characters, of course, to land. To model the gravitational forces acting on the ship as they approach a planet, we examine two cases: the Millennium Falcon near Hoth and Luke's X-Wing near Dagobah. In both scenarios, we will consider the spacecraft to be 1,000 kilometers away from the planet. According to Wikipedia, the mass of an X-Wing is 10 to the 4th kilograms, and as there is no canonical mass for Dagobah, a real-world analog is needed. Dagobah's diameter of 14,410 kilometers closely approximates Earth's diameter of 12,756 kilometers, as we can see here. Thus, in the absence of any contradictory lore, it is reasonable to approximate that the mass of Dagobah will be close to the mass of Earth, which is 5.972 times 10 to the 24th kilograms. And then our planetary radius, of course, is half our diameter, which is 7,205 kilometers. Thus, the distance between the ship and the planet's center, R, is the radius of Dagobah, plus our assumed distance of 1,000 kilometers, which is 8,205 kilometers, or 8,205,000 meters. And thus, applying our formula, we get that the X-wing would be facing a gravitational force of 59,168 newtons when it's 1,000 kilometers away from Dagobah. By Wikipedia, we can get that the mass of the Millennium Falcon is 1.5 times 10 to the 5th kilograms. And like Dagobah, Hoth has no canonical mass either, so we again adopt a real-world analog. Its diameter of 7,200 kilometers, it closely matches that of Mars' diameter of 6,792 kilometers. Thus, we can once again approximate that the mass of Hoth is close enough to the mass of Mars at 6.417 times 10 to the 23 kilograms. The planetary radius, of course, is half the diameter, so 3,600 kilometers. And again, our distance from the Falcon to planet center is the radius of Hoth plus our assumed 1,000 kilometers, which gives us 4,600 kilometers,